Hello, my name is Matt Eden, and I'm a graduate research assistant for Dr. Tan Veer. Now, this video is going to be all about how to create a custom robot chassis in a CAD software. In this case, we're going to be using Solidworks. How then to import that custom chassis into ROS, and then how to be able to control that with your simulations using all kinds of different methods of control. So there are a bunch of tutorials out there, for taking in existing things, but this is all about how to use something for a custom robot. So here, this first thing I want to show you guys here, this is a basic example of something that I've been working on. It's not perfect at this point, but this is just a good demonstration. So I'm going to go ahead and I'm going to make this transparent. Here you can see I have a very, very detailed model. And this is not what you want to use in terms of simulation. So one of the first things I want you to understand is it's a very good idea to make a very detailed CAD model of the system that you're trying to design. That being said, it is not a good idea to have something this detailed that you're actually going to be importing. You're going to want to make sure that you have two versions of whatever you're creating: your detailed version and then your simplified version, where your proportions are the exact same, but you don't have any of this detail because your simulation time is going to be just crawling. So especially the tread on these tires is preposterous in terms of being able to actually accurately simulate that time. So what we're going to do is we're going to create we're going to start with just a basic design. Also, too, we're going to be using a four-wheel design here and doing a two-wheel, design for a differential drive robot is also very, very similar. The process is the exact same. But I'm going to go ahead and I'm just going to make a new part. We're going to start off with even though this is a laser cut chassis that's meant to be put together, I'm just going to create a single piece, and we're going to create something just kind of general here. So like we said, our goal here is to create a very, very simple chassis that we can use just for representation. And so we want to make it, the exact same dimensions of what it is we're creating, but we want to make this much more simplified. So what I'm going to do here is I'm going to go ahead and I'm going to just sketch something out. And let's say my robot chassis is going to be 12 inches by 12 inches. Also, too, it is a good idea when you're designing a custom robot chassis to make it as square as possible. Oops. Okay, awesome. So that looks great. Let's go ahead and extrude this guy out, and we'll make it 5 inches. Sure, that looks good. Okay, awesome. Now, this is supposed to be, like I said, a gross oversimplification. And so what I'm going to do is I need to make sure I have something that I can connect to my simplified wheels too. So this would normally, you'd mount your motors and you have a motor coupler and a wheel and all of that stuff. But I'm going to go ahead and I'm going to make this really, really simple. Let's make this a 1/4 inch here. That looks good. And then, okay. Now here, this line, also too, you could make that, oh, sorry, excuse me. Make that for construction. Not that that really matters. Okay, so all I did here was I just wanted to make something to mirror. So that way, if I need to make changes later, I can. So here I have, right, my circle. I've mirrored it over there. And again, that's just to save me some time. Okay, so that looks pretty good. Let's go ahead and we're going to exit our sketch. And we can change this later. 5 inches is crazy, but let's go like 2 inches. We'll probably make that smaller later too, but it doesn't really matter. Okay, awesome. So let's go ahead. Actually, here, I'm going to go back into that sketch. And I just realized we didn't really dimension how far this was away. Oops. Okay, let's make this, we're going to keep this just nice and simple numbers. Also, now you can see my other side is moving as well over here, which is nice. One of the reasons why it's a good idea to mirror. Okay, perfect. That'll work. Okay. All right, awesome. Now, I need to reproduce this on the other side. There are several ways that I could do this, but let's have some fun here. Okay, so let's see if we go here, All right, and then convert entities. This is honestly probably more trouble than it's worth. Oh, I was hoping to go through here. Okay, honestly, no, we don't need to worry about that. Okay, excuse me. In this case, it might actually even be quicker just to do this again on this side. Also, too, I know I'm going a little bit fast here. This tutorial is assuming that you have some SolidWorks experience. I know a lot of you guys probably do. This isn't meant to be a full-blown SolidWorks tutorial. If so, we can go into more detail later. But also, this isn't meant to be your very first ROS tutorial either. Yeah, we're kind of operating here under the assumption that you've had some general ROS experience as well as some general SolidWorks experience. Okay, perfect. All right, so let's take a quick look here. Okay, that looks pretty good. Okay, again, we can change all that stuff later, but here we have our basic shape. Okay, so I'm gonna go ahead and I'm gonna create another new part, and you want to make sure that you are measuring your wheels and things. But I'm just gonna go ahead and I'm gonna make this, let's make this like a 4-inch wheel. That's probably pretty close. Okay. Sure, that'll work. Okay. Now in this case, I'm gonna make this exactly the size of that shaft. So I believe that was 0.25. And I'm going to, let's just bring this in just like 0.5 inches, maybe something like that. Okay, great, looking good. Okay, if we wanted to make this look a little bit more wheel-like, we totally can. We can add here, I don't know. Really, it's not super necessary. Okay, so we're going to start with that. We want to keep this as simple as we possibly can. So I have a wheel and I have a chassis. So I'm going to go ahead and I'm going to make an assembly. Oh, I didn't save that stuff. Okay, sorry. 1 second, guys. Okay. Not that it really matters here, but if you have it saved here and you keep these open, then whenever you go to insert components, it makes it very easy. Not that, it's that hard in general. Okay. Now I know there's a hotkey here to copy, but this is fine. Okay, great. All right. So let's see how our proportions look here. So I'm gonna go ahead and what we want to make sure we do is we put put the correct mates on here. So you want to use as few mates as possible. And so, as I'm sure you guys are aware, whenever you're creating mates in SolidWorks, it's not really about adding movement, it's about restricting movement. So you say like, I need this face to always be touching this face here and things like that. So what I'm going to do is I'm going to go ahead and I'm going to want to mate edge to edge as often as I can. So I'm going to go like edge here, making sure you're not clicking on that face. And edge. And honestly, I think we should only need one mate. Okay, now that is hilariously tiny. I think we should definitely go change that. What do you guys think? That wheel is way too small. I apologize. I didn't measure my actual dimensions of my things. I was just kind of simulating this. But here, let's go ahead and edit this, and then let's go like 6 inches. Thankfully, all of this stuff. There we go. Okay, that looks a little bit better. Let's go ahead and make that smaller too. Okay, perfect. That's honestly that's still not perfect, but I just said it was perfect, but that'll do for now. Okay, let's go ahead and meet the rest of these guys. Okay, again, making sure I'm clicking my edge. Also, too, I wanted to mention, depending on your processing power, you can add more complexity. So, like if you wanted to add in a manipulator and things, um, I've found that that is totally possible to include. Right now, I'm running on a VM, so I have to be a little bit careful. But if you're running on native hardware, if you're running Ubuntu on actual computing hardware instead of through a VM, and you can probably get away with more complexity. But also, then it would take longer for you to watch me model all this, and so that's not what we're going for. Okay. All right. So here I messed that last one up. Let's go ahead and let's flip. Perfect. Okay, looking pretty good. Again, we have our general purpose robot chassis. It looks pretty boring, but that's okay. All right, so there is much more that we have to do. We can't simply just export this into ROS. Well, we can, but there are several steps we need to take. So as I'm sure you guys know, we absolutely need a URDF file. And so, what's nice about SolidWorks, and there are some other CAD softwares that also have URDF exporters. I think there's an Onshape one. I'm pretty sure there's a Fusion 360 one. But as far as I understand, you guys have SolidWorks licenses at Kennesaw, so I would just stick with this. And the installation process is really, really straightforward. And as soon as you go through that installation process, under the Tools tab, if you go, and for me, it was all the way here at the bottom, there is export as URDF. Now, there's a lot of things you need to do to prepare for this. You can't, so it's not super easy. You just like click one button. There's a couple things that we need to do. So, as I'm sure you guys know, in your URDF file, we describe our robots using links and joints, and so we need to set that up to make sure we have the highest level of success. So, we're going to start with some reference geometry. So, I'm going to start with a point. Now, by default, your point will be center of face. So if I click on this face, you'll see by default, it put it right in the center of the face, which is perfect. That's exactly what we want. Now, at this point, we need to pick our orientation. So I'm going to go ahead and say that that's back right, front left, back left. So we're going to see that, honestly, it's as annoying as it is, taking the time to name this stuff is really, really important. So we said that was back right. So back right. No, here we're gonna do this to BR point. Okay, so we have our point. Now next we need an axis. So if I click on axis, what's really cool is if I click on this face, it will automatically put that axis right there because the point is already selected. Do you see that? So it just that's just the order I like doing this stuff in. And so there we go. So I'm going to go ahead and I'm going to rename this BR axis. Okay, I have an axis now. So that's going to be my axis of rotation. Okay, next, there's one more bit of reference geometry. We need a coordinate system for each piece. And so by default, it's over here for some reason. But its position, you want to make that point. Boom. Perfect. Okay, so now we have it in the right spot, but this orientation is not correct, not at all. So if you see here, Y is up, right? And ROS has the convention where X is forward, right? So like X should be in this axis, Y should be facing this way, and Z should be facing that way. So over here is where you change the orientation of this piece. I usually like to clear my selection here, and I want to add as few dimensions as I possibly can. So I'm going to start with Z, and I need to just click on anything that's in the Z axis. So like this line is absolutely with the Z axis. So I'm going to go ahead and go here, right? That didn't work. Okay, awesome. So Z is now pointing correct, but X is absolutely not. So I'm going to go ahead, and for the X axis, I'm going to go like that. Okay, perfect. So now you can see. Also ignore this. This is your document here. But now you can see Y is pointing to the left. I have X pointing forward, and then I have Z pointing up, which is exactly what I want. So I'm going to go ahead and I'm going to rename this BR CS for coordinate system. Okay. Back right point, back right axis, back right coordinate system. So now you want to make sure you do that for all 4 of the wheels, making sure your coordinate system is the exact same. Okay, so here we see we have all of our coordinate systems and points set up in our axes here. So okay, so you can see X is facing forward, X is facing forward, X is facing forward, and X is facing forward. Okay, so I did want to show you guys, if for whatever reason you need to play around with these a little bit, just know that you can flip these buttons and things. That can make this really, really easy. So it may take you have to play around with it for a little bit to get it right, but know that you can flip the orientation and select the different edges in order to get that right. Also, too, I wanted to show you by default this is usually collapsed, and so if you're having trouble being able to click your point, because normally it's listed over here, just know you can drop this down and then click your point that way. I wasn't sure if I said that before or not. So now we look good. Okay, so we actually need to put in one more point and coordinate system. And this is going to be really, really important because this is going to be our base of our entire system here. So what we're going to do is we're going to create reference geometry again. We're going to start with a point here. And now this is going to be a fixed joint because it's our base, basically, the base of our entire thing. So we don't need an axis, but we do need a coordinate system here. So perfect, we're on 0.5. Okay, the x-axis is going to be this way, and let's flip it here. Okay, now z still isn't right. Honestly, this arguing with this system can be kind of annoying, but it is definitely possible to get it right here. Okay, there we go. Awesome. All right, so again, took me a couple tries there, but I have x going forward, y going over to the left, and z going up. Awesome. Okay, so here, 0.5. I'm actually going to move this to the top here. Let's see. And move this guy right there. And the reason why I did that is because this needs to be the base of everything we're doing. So base point and base CS. That's what we'll do here. Base CS. Okay, and even though that seems like it's very, very tedious, you're going to see that it's going to make the next process much, much easier. And so we are actually good to go in order to create our URDF. So we're going to go over to Tools, Export as URDF. Now keep in mind, guys, you do have to install this plugin. The installation process is very, very, very easy. So just know that if you don't have this option, that means you haven't installed it yet. Just so you guys know, too, I'm running SolidWorks 2022. I'm pretty sure like the actual supported version might be a version or two ago. Like 2020 or 2021, I can't remember. But just know that for 2022, it's working fine for me. I imagine 2023 also, or 2024 will be totally fine. I haven't tested it myself, but I mean, it's just not really a big deal. Okay, so I'm going to go ahead and click Export as URDF. Okay, now by default, this is base link, and you should absolutely keep this convention the exact same. So one of the first things you have is the origin coordinate system. Now by default, this says on automatically generate. That is not what you want to do. You want to click on your base coordinate system. Now here in this box, you need to select, the objects that are a part of the base. And so you're going to hit this drop-down menu, and this chassis is the base, and so I'm going to select that. Okay, so I want to mention too that this format, or the way that I set up this document is going to be incredibly similar to if you were doing a robotic arm, but with one key difference. So with a robotic arm, each link builds off of the next because they're all connected. But here, this 0 here, this is the amount of child links that you have. And so because this is a rolling robot, we want 4 links that are not cascading. All of them are connected to the base link. So that's going to be very, very, very important. So now what we're going to do is we're going to click on our empty link. So I click on empty link, and that's a terrible name. So I'm going to say link, and let's do the same way we started before. So we started with the back right. So link BR, and we're going to use the same convention, joint BR. And again, coordinate system. Here we go. We just click on BR. Now the joint type, we're going to make continuous. But you guys see how easy that was? So now if those were all just numbers, if you didn't change the temp, it would take a second to remember which one was which. And so now we can be totally sure. So there we go. This wheel, that would be our back right. So I'm going to click on this guy. And so that is good to go. So now over here, let's say link FR for front right. Joint FR for front right. Axis coordinate system. Continuous. There we go. Verified that that is the correct one. Okay, we are getting there. So let's see here. Front left. Let's do that one. Joint front left. Also, too, guys, I'm putting the underscores in here only because we're going to need to reference this in software later. So I'd recommend doing that, just so you don't have any issues down the road. Front left, continuous. There we go. Oh, whoops. Oh, did you guys see that? Here, look, we created a bunch of extra links under front left. That's not the way it's supposed to be. Okay. Let's double check that before we export this. Okay. Back left. Okay. Awesome. Okay, this is looking pretty good. Okay, so let's see here. We're gonna click on these just so we are sure. Okay, so we make sure they all match. BR. Okay, and then this guy is highlighted blue. Front right. FR. Perfect. Front left, and back left, which we just did. So we got BL. Okay, awesome. We're good to go. So next, we're going to hit preview and export. Awesome. So here we see there is nothing, but you do want to make sure. So like it looks like there's nothing under joint BL, but it's actually not selected. So you want to make sure that you see this, you see this, you see this, you see this. Okay, there should be things under everything. You see, okay, perfect. Now there is one thing that you absolutely positively need to change. I want you to take a look at the y-axis. So I do not know why, but by default, it changes to -1 on the left side. And I think it's probably just because it knows it's flipped, but that will mess up everything. And so you want to make sure that you change your negatives to positive, just on that one axis. So now, if you look at the y-axis, it is 1 for all of them. Perfect. They all say continuous. That is great. That is all you need to change. Okay, next, we want to make sure that our inertials are right. So I'm going to click on all my links, and it does not really matter what they are, so long as they are not, so long as they're not 0. Okay, look, that actually, no, that's fine. Okay, I was going to say, I thought that looked a little bit strange, but we're fine. Okay, so that all looks fantastic. All right, so that is looking pretty good. I'm going to go ahead and I'm going to say export URDF and meshes. The meshes, those are the actual, the STL files. And so I'm going to say export. Now, this is super, 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 super important. This is going to be the name of your actual ROS package. So this is not only going to create a URDF for you, it actually creates the full ROS package. And so I'm going to call this, I don't know. I just have a lot of robots that are like simple chassis or something here. Let's call this MTRE for the master's program. So MTRE bot. How about that? Okay, perfect. All right, so it creates the URDF package. Now, keep in mind, I actually saved this in my shared file for my virtual machine, but you can then put this on a flash drive and then put it onto your Linux machine or whatever it is, however you're doing this. Okay, don't worry about this. And we should be good to go, but now we need to test it. So I'm going to go ahead and I'm going to hop over to the virtual machine and I'll show you guys how to proceed to the next step. Okay, guys, so here I am in my Linux environment, and so if we want to get this sucker working with ROS, we need to actually compile. So you're going to do this the exact same way, using CMake as if you add any package. You do need to compile this package before it's good to go. And so okay, so we call this guy MTRE. Let me see. Okay, MTRE bot. I'm going to go ahead and move this to my home folder and my Catkin workspace into the source folder. Okay, awesome. So I have a bunch of stuff in here, but now I see I have my MTRE bot here in my main Catkin workspace, just like I would with any other ROS package. So let's go ahead. Let's go into here. And I'm going to compile. And whether you're using Catkin build, Catkin make, doesn't really matter. That's just how I set up this folder with Catkin make. Perfect. Okay, so it looks like it compiled just fine. Okay, so let's go ahead and we're going to source our workspace. Okay, Catkin source, and I like to fully navigate there first once just to make sure I'm good here. So cd mtre bot. Okay, now what's really cool is it creates a launch file for you already. So I'm gonna go ahead and go into that launch file. Okay, so we have gazebo.launch and display.launch. So display will open up RViz, and Gazebo will open up Gazebo. And so I'm going to go ahead and launch this. Okay, hopefully we don't run into any issues here. Oh my goodness, look at that. Okay, so here is our robot. And so we have successfully loaded this into Gazebo for simulation. Now, that being said, we do not have the ability to move this robot yet. And so that's what we need to do next. And thankfully, the process actually isn't very difficult at all. But that's what we're going to talk about next. And so as you guys know, there's several things that we need in order for this to fully work here. So I'm going to go ahead and let's see here. ROS topic list. Okay, here we go. So we don't see any of the things that we normally associate with, being able to actually move things. We don't have TF. We don't have some of the other things that we need. Actually, we do have TF, but that's not what we need. So we don't have the things that we need, and you can tell that by this ROS topic list. And so, thankfully, what's cool is it's actually very, very easy to add. So there are Gazebo plugins that are designed to help with this. And so I'm going to show you guys how to do that now. Okay, perfect. Okay, so I'm just going to open up just a Chrome window. And so what I want you guys to do is search for Gazebo plugins. And it's actually the first thing that you see. So here's this Gazebo plugins in ROS. And so what's cool is there's actually a bunch of different plugins that you can do. And so we're going to go all the way down here, and we will find one for a diff drive robot or a skid steer. Okay, so like I was saying before, the diff drive is actually really, really straightforward. So these are built-in controllers. You could absolutely create your own controller from scratch, and in fact, in some ways, that's a very good thing to do. But what I'm going to do is I'm just going to go ahead and grab this because this is what we need. So again, this file name, this is built in that joint controller, so it makes it really, really, really straightforward. Okay, so perfect. And so this is actually going to be pasted into the URDF. Okay, so I'm going to go over to mtrebot, URDF, my URDF file. Okay, and so this is what was automatically generated by Solidworks or the URDF exporter. So you can see it did create STLs for our different options and gave us the inertials and things. So I'm going to go all the way down at the bottom. Okay, so before the last robot tab, I'm going to go ahead and paste this Gazebo plugin. The tabs really don't matter, but we want to make this look good. Okay, so this stuff we keep the exact same. We should not need to do this. I'm going to keep this stuff the exact same as well. Honestly, it probably doesn't match our actual robot, but it's pretty straightforward. So this is your wheelbase and the diameter of the wheel itself, which we could absolutely figure out. In fact, if it acts wonky at all, we'll go back and change it. But okay, so here we can see that we're actually we're subscribing here to command velocity. That's what we need to actually be able to use this guy. And so that's going to help us here in terms of actually being able to control this with something like, well, you can just now send any twist messages you want. So you can generate twist messages from like your LiDAR script, or you can generate twist messages just from a regular Python, node if you want to. And there's a bunch of things. So we're just going to use teleop twist in this first example because that's really straightforward. But there are things that we do need to change. And so you'll notice our joints are not like this at all. So we used a completely different convention for our joints. And so we did, oops. Ours were joint FL. And again, this is what makes it so nice when you take the time to measure or to name things in a way that makes sense. Okay, so that's front right. Also, too, in case you guys weren't aware, I'm just using VS Code here. VS Code works really, really well, especially with in these Ubuntu environments. And so, okay, so back left. Okay, they use rear instead of back, which probably makes more sense actually. Okay, there we go. Back left. So maybe we should use that convention next time we do this. Back right. Okay, that looks good. All right, awesome. And that should be everything that we need. Okay, so let's go ahead. And recompile. Okay, perfect. Didn't change much, right? Okay, so we're going to resource. Okay, so now let's see. Okay, so since we've already found it once, you can see we don't even need to navigate back into our folder here. And it should just be gazebo.launch. All right, now fingers crossed, guys. Hopefully we don't have any weird errors. Okay, awesome. So now you can see the skid steer is working properly. That's kind of cool, huh? Okay, looking pretty good. And now I'm going to ROS topic lists. Sure enough, we see ODOM now, and we see command velocity, all of that nice stuff. Okay, so now I'm not sure if you guys have used Teleop Twist yet or not, depending on where you are in your courses and things. But the Teleop Twist node or package, however you'd like to describe it, is actually just a Python script. So we're not going to do ROS launch. So we're going to do ROS run Teleop Twist, and I just auto finish there. So I just did tele, and then I'm gonna hit tab again, teleop twist keyboard dot py. Okay, and then that will run. And so here we can use I, K, J, L, and then the comma here. So here I'm gonna go ahead. I'm gonna press I, and look at that. Our robot is moving. Okay, perfect. So now I'm gonna do a little spin. Here we go. And so now we have our robot fully simulatable. Like I said, there's a million different ways you can create twist messages. And what's really cool too, this is something that I end up doing a lot in my research, is creating a script that will convert those twist messages, subscribe to the twist messages, and then send those via UART to a microcontroller that's then controlling your motors. And so this is a really great way to go from a robot that you can visualize here, and then also be able to control physically. So then you can remote in, and you can create really complex robotic systems. And so this is the first step to a lot of really, really awesome robotics projects. Whether you're just going to be simulating something, or you're going to be do something, you're going to be creating very complex things, or just simulating, or whatever you're doing. This is the first step to being able to do some really, really awesome stuff. And so here you can see everything is working the way that you think it should be. Now, if you guys remember in that URDF, those dimensions in terms of wheelbase and wheel size were completely wrong. And so this is, you should absolutely be making sure that your simulations match your actual parameters. But in this case, I figured it would not really, it wouldn't really slow us down. And so, so there we go. All right. Hopefully you guys found this helpful. Again, the process for doing this for a robotic arm is also really, really easy. And it's a very, very similar process. You have the extra step of having to use ROS move it. But other than that, it's not too tough. So I hope you guys found this helpful, and I wish you guys all the best of luck on your robotics engineering journey. Thank you so much for watching.